Okay, good morning. So we're looking at bacterial transformation today. And as a key part of that, we need to understand what a bacterial plasmid is, because plasmids are a really important thing in the process of understanding bacterial transformation. So just as a reminder, I've got a diagram of a bacterium here, and it's got its circular chromosome in the middle, so just the single chromosome there. And it's also got these small loops of DNA, and that is a plasmid. So they're small loops of DNA found in bacteria, and they often contain genes for restriction enzymes, as well as genes for antibiotic resistance. Okay, so that's what a plasmid is. And like I say, when we're understanding bacterial transformation, understanding plasmids is really important. And plasmids essentially act as a vector, so a way of transporting the DNA that we're interested in. So I said there that they can be used as vectors, ways of transporting genes, and plasmids can be used to make what we call recombinant DNA. So recombinant DNA is DNA from two different sources. And yeah, we can also use plasmids to clone genes as well. So we're going to take a look at how we can clone a gene using plasmids. So the first thing we want to do is we want to cut out the gene that we're interested in. So for example, let's say that we're trying to clone a gene from a human. Quite a common example is insulin. So let's say we're trying to clone the gene for insulin so we can get lots of insulin for people who suffer from type 1 diabetes. So the gene that we're interested in is cut out using restriction enzymes. Okay, apologies if the light's disrupting your reading. We cut it out with restriction enzymes, and the exact same restriction enzyme is also used to cut open a plasmid. The reason for that is if we use the same restriction enzyme to cut out the gene from the human and the same restriction enzyme to cut open the plasmid, it should make complementary sticky ends, okay? So it should make sticky ends that will easily go together because they can contain complementary bases, all right? We then use DNA ligase to basically join the plasmid into the gene. And we call that recombinant DNA when that's happened because it's, so I've mentioned there the recombinant plasmid, and it's called recombinant because it's obviously a bacterial plasmid that's had a gene from another source inserted into it. So we've made our recombinant DNA. We then reinsert the recombinant plasmid into the bacteria, often using what we call a heat shock, which is basically where we make it really cold and then really warm very quickly. And what that does is that just makes the cell wall and the cell membrane of the bacteria much more permeable, allowing the plasmids to get back into it, hopefully. And then what we do is we allow the bacteria to reproduce, and as it now has a new gene, it makes the product of that gene as it reproduces. So in diagram form, this is not to scale. I've got my cell here, so we've cut out a gene from that cell using restriction enzymes. The exact same restriction enzyme has been used to cut open a bacterial plasmid. We've joined them together using DNA ligase, making our recombinant plasmid. We have put the recombinant plasmid back into the bacteria. Then the bacteria is growing and dividing, and it's producing the product of that gene as it does so. Okay? So that's called gene cloning because the gene that we're interested in is being cloned many, many times just by the bacteria reproducing. And like I say, that's really helpful because it can make a product very, very quickly. Like I say, a quite common example is using this method to produce insulin. Before we made this method, the only way to get insulin for type 1 diabetics was to harvest it from pigs, because pigs produce quite a similar form of insulin to humans. And that has its own issues. You know, it's not as efficient. It's not very fair on the pigs because you have to kill the pig to get their insulin. There are some religious objections to using a product from pigs. So all in all, using pig insulin just wasn't a great solution for a number of reasons. So this method of getting a human gene, inserting it into a bacterial plasmid, and allowing the bacteria to grow and multiply and produce insulin as they do that was a much more effective way of making insulin. So that's how we do that now. So That process can also be called bacterial transformation. So once the recombinant plasmid has been taken up by the bacteria, we say it has been transformed. And in this case, that just means it's got DNA from another source as part of it. I mentioned there that this gene cloning method can be used to produce insulin for diabetics. It can also make lots of other proteins that are important for various reasons. Human growth hormone, for example, is made in this way as well. And it also can be used just to make more copies of a gene that we want to study, although that's quite rare now because if you just want to make copies of the gene rather than make the product of it, the polymerase chain reaction is much more efficient and effective. But theoretically, there's no reason why you can't use this gene cloning method just to make more copies of a gene to study. And the final thing to touch on for today is that viruses can also be used as vectors to insert DNA into a bacteria after transformation. So we can put DNA into a virus. The virus will then insert its DNA into a bacterium, and it will use the machinery of that bacterium to replicate. And as it does so, it produces new copies of the gene as it goes. There is a diagram of that in your slides as well. So quite a quick lesson today, but just to go over the really important things to really understand is what's meant by recombinant DNA. So that's DNA from two different sources, like when the plasmid has the human gene inserted into it. We need to understand the 4 steps of gene cloning. So that's cutting out the gene and cutting open the plasmid using the same restriction enzyme, stage 1. Joining the plasmid and the gene using DNA ligase, that's stage 2. Reinserting the recombinant plasmid into the bacterium, stage 3. And finally, stage 4, allowing the bacteria to grow, multiply, and produce the product of the gene as it does so. Be important as well that we can refer to the bacteria as being transformed after that's happened to it. Be aware that viruses can be used to clone genes as well. And that's about everything for today. So check into the Zoom if you have any questions or clarifications, and make sure you work through the exam questions that I set as well, and have an awesome weekend if I'm teaching you on the Friday, and have a good start to the week if I'm teaching you on the Monday. Okay, have a good one.